So we're getting started on a new chapter, and a new chapter means new definitions. A solution is a homogeneous mixture of two or more substances. So two or more things have to be in a solution. A solution composed of two different things. One of those things is going to be a solute. A solute is the thing in a solution that's present in the smaller amount. The solvent is the thing that's present in the larger amount. Solution has to have at least two things, and at least one of them is going to be solute, one's going to be solvent. You can have more than two things as well. So back when we started naming compounds, we first identified whether we had an ionic compound or a molecule, a molecular compound. Ionic compounds were metals and nonmetals. In a solution, ionic substances typically dissolve in water. Typically dissociate when they dissolve in water. Dissociate means break apart. A molecule typically does not dissociate when they dissolve in water. So there are exceptions to the ionic substances, but here's what an ionic substance dissolving in water looks like. Solid sodium chloride. You add some water to the mixture, you get sodium ions and chloride ions. Those two things separate, dissociate. This little AQ, that tells you it's aqueous. It is dissolved in water. So chapter 4 is all about reactions in aqueous solutions. These physical states, solid and aqueous, are going to mean more to us now, and we got to make sure we include those in a lot of reactions in this chapter. Molecules typically do not dissociate. So you go from methanol that is in a liquid state, add some water, you get methanol that is in an aqueous state. Methanol that is dissolved in water. This is saying water is the solvent and methanol is the solute. That solute did not dissociate. This is saying water is the solvent, sodium chloride is the solute, and that solute dissociates into those two ions. Something else about things that dissociate. When something dissociates, it often can conduct electricity. Something that can conduct electricity is called an electrolyte. Something that cannot conduct electricity, non-electrolyte. So non-electrolyte in this beaker down here, light bulb is not on. Strong electrolyte, light bulb on. Weak electrolyte, light bulb on but not very bright. So electrolytes tell you how many ions are in solution, or electrolytes have ions in solution. And if it's strong, it means it has a lot of ions in solution. The more ions you have, in general, the brighter that light bulb is going to be. It gets a little more complicated than that, but that's what we're going to say. So we need to be able to identify whether a solution is an electrolyte or a non-electrolyte. Which of these is an electrolyte? Something that's strong electrolyte will absolutely conduct electricity. A strong electrolyte means 100% dissociation. That word strong means completely broken apart. Sodium chloride is a strong electrolyte. It dissociates completely into sodium ions and chloride ions. A weak electrolyte is not completely dissociated. Only a small bit of ions are freely floating in solution. Something like acetic acid, that's what this is, acetic acid. It gives you some ions in solution, but it does not give you complete dissociation. That arrow right there tells you it is a forward and reverse reaction happening, not completely dissociated, a weak electrolyte. Ugh. Okay, more definitions. Hydration, the process in which an ion is surrounded by water molecules arranged in a specific manner. So if you dissolve sodium chloride in water, the sodiums are all positively charged cations, and they're going to associate with water in a certain way. So water is a polar molecule. We're going to draw Lewis structures and talk about dipoles and all that stuff way later in chapter 9 and 10. But water is a polar molecule. It's got electron density gathered on one side of it. So when a sodium ion is in solution, it looks like this picture on the left. This little sodium ion, all the oxygens of water are pointed toward this cation, whether it's a sodium or a different cation, it doesn't matter. All of the hydrogens in water are pointed toward the anions in solution. The process of the hydrogens aligning toward the anions and the oxygens aligning toward the cations is called hydration. That can be called solvation if it's a different solvent other than water. Okay. Anions are always connected to by water, always pointed to by water. Cations are always pointed to by oxygen. Okay. So we said non-electrolytes are things that do not conduct electricity. The reason they don't conduct electricity is because you have to have ions freely swimming around in solution to conduct electricity, to transfer electrons. But non-electrolytes don't do that. They don't have cations and anions in solution. That molecule from the very beginning slide, that methanol does not dissociate. So if you have a solution of methanol, it will not conduct electricity. Not at all. If you have a solution of methanol in water, it will not conduct electricity. But if you put sodium chloride in water, you can get electricity. You can get a current to flow through that water. So the methanol molecules could still be hydrated. See how this oxygen is pointed toward the hydrogen of methanol, and this hydrogen is pointed toward the oxygen of methanol? That methanol can still be hydrated, but it is not dissociated. It is not two distinct pieces. It's completely intact. Just one molecule of methanol is further separated from a different molecule of methanol when it dissolves in solution. Whew. This is another one. Does not dissociate. Nope, not at all. In fact, this one is too unlike water that it doesn't really even dissolve in water. You get two separate layers when you put hexane in water. Okay, so acids. Acids are a thing we're going to talk about quite a bit in this chapter. Acids are molecular substances which ionize in water. Okay, cool. So what? Acids could be considered strong, or acids could be considered weak. Just like a strong electrolyte means 100% dissociation, a strong acid means 100% dissociation, generally speaking. A weak electrolyte means not 100%, it means some dissociation. So a weak acid means some dissociation. Acetic acid is what's known as a weak acid because it dissociates some to produce some ions in solution. And that reversible arrow, we said before, is an indicator of a weak substance. This is a weak electrolyte, also known as a weak acid. So we said molecules, that's nonmetals. Molecules generally do not dissociate in water. Some special molecules do, special molecules known as acids. But right now, we're about to put a pin in acids and not talk about that anymore. We're going back to ionic substances. Ionic substances generally do dissociate in water. There are exceptions, but ionic substances are metals and nonmetals. Which ones generally do dissociate? In general, the rule is, if you have a +1 or a -1 charge, that compound will dissociate in water. So this is sodium phosphate. You knew that, right? You remember naming compounds? Oh, can't forget that. Sodium phosphate. Sodium has a +1 charge, and phosphate has a 3- charge. Because one of these things has a +1 charge, it means this salt, this ionic substance, is termed soluble. Are there any exceptions to this rule? There are a couple. Not a lot, but a couple. Silver chloride is an example of an exception. That's a +1 charge with a +1 charge, not soluble. Lead iodide is an exception. Iodide is a -1 charge. That's an exception. Hydroxide, a lot of hydroxides are insoluble if it's partnered up with a +2, a 2+ cation. So in general, if either of the partners of your ionic compound are a +1 or a -1, it's soluble, but there are exceptions. Okay. If you have a partner pair that's greater than one positive and negative charge, where both ions greater than one positive or negative charge, it is generally not soluble. So you put calcium sulfide in water, you get calcium sulfide that sunk to the bottom, did not dissociate, did not dissolve in solution. One exception to that is magnesium sulfate. If you put that in water, it still will dissociate. So here's an organized table to tell you about solubility rules. These are solubility rules that you need to know / memorize, and I hate the word memorize, but there are some unfortunate things to memorize. These compounds up here are soluble. That's a +1, -1, -1, -1, -1, -1, -1, -1. Yep, soluble. This sulfate is also soluble a lot of times. Almost all sulfates are soluble. There are exceptions. Some sulfates are insoluble. Almost all +1, -1s are soluble. There are exceptions, and we've already pointed out silver and lead as two of the exceptions. Most +2, -2s are insoluble when they're partnered up with something that's also +2, -2, +3, -3. If you have alkali metals, remember that's the first column of the periodic table, lithium, sodium, potassium, rubidium, cesium. If you have an alkali metal with these, they're soluble. If you have an ammonium ion with these, soluble. Most of the hydroxides are considered insoluble, except for alkali metals. We gotta know the alkali metals. Sodium, lithium, potassium, rubidium, that kind of thing. Barium hydroxide is also considered a soluble exception. So, our last slide said the rules are if you're +1, -1, generally considered soluble, if either partner is +1, -1. If both partners are greater than +1, -1, probably not soluble. The exceptions that I point out to those two rules are these: the sulfates and the hydroxides. So, taking those solubility rules into consideration, do you write this thing as soluble or insoluble? Well, that's barium 2+, and nitrate 1-. 1-, soluble. So you separate those ions. There's a 2 out front for the nitrate because barium nitrate itself has 2 nitrate polyatomic ions, but when it dissociates, you get 2 moles of polyatomic ions out of that dissociation. They're both aqueous. Potassium hydroxide, soluble, not soluble? Soluble. Hydroxides, a lot of them are not soluble, but potassium is one of those alkali metals. It's soluble. You get a K+ and an OH-, aqueous. Calcium phosphate, that's a +2 and a -3. Not soluble. Magnesium chloride, that's a -1, soluble. Yep. Lead iodide, that's a -1. Makes me want to say soluble, but this is one of those that's an exception to the solubility rule. So in Chapter 4, we will do 3 major classes of reactions. And those 3 major classes of reactions are precipitation reactions, oxidation-reduction reactions, and acid-base reactions. We're starting with precipitations, and in order to determine whether a precipitate will form, you need to know the solubility rules, what's soluble and insoluble. What we will do most often is we'll have 2 solutions that are soluble, 2 solutions that have soluble ions in them, pour those 2 solutions together, and see if they form a solid. If they do form a solid, we'll do a lot of mathematical stuff with that, like which was the limiting reactant, how many grams of product did you form, et cetera, et cetera. So, get to know those solubility rules early. When we write these solubility equations, these precipitation equations, I said we would generally have 2 solutions that are considered soluble. This is an aqueous solution that has lead 2 nitrate dissolved in it. So nitrate is a -1. Nitrate is a soluble thing. So this dissociates into Pb2+ and 2NO3-. That's what would be in a beaker that had lead nitrate in it. Sodium iodide is also a +1 and a -1. It's not an insoluble exception. So we would see, that's supposed to be an I-. We would have a beaker that has free-floating ions of sodium+ and I- in it. So when we pour these together, you give these ions in each of these solutions a chance to swap partners. So the lead and the iodide come together, and the sodium and the nitrate come together. How do you know who should swap partners? The cations and the anions do a little do-si-do, swap places. When lead and iodine come together, they form an insoluble solid. Remember, that was one of the exceptions to the solubility rule. But when sodium and nitrate comes together, they remain soluble. So this test tube over here, this pipette up here is dripping in one of those solutions and creating this yellow swirl of lead iodide in solution. One of the things that students find the hardest in Chapter 4 is writing these kinds of equations. We will see several kinds of equations in Chapter 4. If it's a solubility equation, you got to know if your reactants are soluble or not, and you got to know if your products are soluble or not. This one is not soluble. That will precipitate from solution. Okay, so a molecular equation does not show charges. Everybody's paired up in a molecular equation. In a complete ionic equation, you break down all the things that are considered soluble. So I told you before, lead nitrate is considered soluble, so you break it down into its ionic pieces. I told you sodium iodide is soluble, so you break it down into its ionic pieces. Lead iodide is not soluble, so it stays the same. And sodium nitrate is soluble, so you break it down into its pieces. Complete ionic equation shows all ions on both sides of the equation. And then you can go through and cancel out anything that's exactly identical on both sides. I've got 2 nitrates on the left. I've got 2 nitrates on the right. I've got 2 sodiums on the left, 2 sodiums on the right. So I cancel out anything that's the same on both sides, and I end up with what's called the net ionic equation. Pb2 plus 2i minus yields Pbi2. Net ionic. That sodium and nitrate that we canceled out in the middle, those are called spectator ions. So, as I'm wrapping up this video, writing equations is one of the things that students find toughest in this chapter. You must practice, but in order to do well on precipitation and solubility equations, you have to know the solubility rules. So the chem activity we're going to do is making you practice some of the solubility rules, knowing what things are soluble and not soluble, as well as making you write molecular, complete ionic, and net ionic equations and recognize spectators. Are you ready? Let's do it.